Guys, I was wondering, what's the overhead of calling a function? I mean, if function A calls function B, then function B calls function C. How much overhead is that compared to function A directly calling function C? Or another way to put it, is it faster to copy the contents of a function instead of calling that function? Let's get started, and let's focus on JavaScript, Python, and Rust. I would like to share with you my computer specs. You can see I have the 11th gen Intel i5. This is not very modern going into 2026, and it's not a terrible chip. It's sort of like somewhere in the middle. So another thing I would like to address is what we are actually going to be measuring. So the most obvious one is the execution time of the functions. So we can just start a timer before we call the function and then see how long that takes to finish once we have finished executing that function. There are a few other caveats that we need to look out for, such as the memory usage of the program. So maybe we somehow have high memory usage and somehow this is making it slower, maybe indirectly. And we also need to be careful about the compilation time. I mean, I will keep an eye on the compilation time. This isn't going to be a primary metric that we are measuring. So we're going to be focusing on JavaScript first, and here I've prepared a small piece of code. When we execute this with Node, we'll be getting about 4 milliseconds. One thing you have to be careful is we are dealing with JavaScript execution. And with JavaScript, there is something called the just-in-time, JIT for short. And I'll show you how this can affect us. If we put this in a simple for loop, we'll just execute it twice, and we can see the results. So here we get about 4 milliseconds again for the first time, and 0.095 milliseconds the second run. And we're going to be consistently getting something like this because of the JavaScript compiler, which is compiling at runtime. And so a bit of background with how the JIT works is that when the code is first executed, the JIT runtime is going to be loading the code and converting the JavaScript into some more optimized representation, such as maybe bytecode of the program. And then this means it can be executed a little bit faster. And on top of this initial compilation, when the program is running, the JIT compiler is often looking at how our program works and is trying to find ways to optimize. With that in mind, there is a chance that when we get to it, our functions could just be optimized away completely. We'll see. We will check this by comparing the speed differences when varying the amount of function calls we make. So here, let's just set this to 10 to see what we are dealing with. And here we get the 3.7, almost 4 milliseconds. It's a lot faster here, but then subsequently we can see the code is running faster, and I believe that is likely because the JIT compiler is seeing how our code is working and is trying to find ways to optimize it. Let's do it once more. And here, I mean, I guess here, maybe not. Honestly, it's a bit of magic how the JIT works, but I think that's the general gist on how it works. So now that we have these results on how long a single function call takes with the hello world print, I've gone ahead and made a generator that generates JavaScript code. And so this Python code can generate 10,000 functions in JavaScript. You can see that we are just pushing out functions that call other functions into this benchmark.js file. Let's go ahead and run this. And we have generated this benchmark.js file. And here we have function 1 called function 2, calling function 3, and so forth until the end, 10,000. And we can copy this into our JavaScript main.js and then add a hello world and then calculate how long it takes to run. And then we can divide this and get how long it takes to call the function. So I've copied those functions across here and added the hello world. And then now we can call function 1 and see how long this takes. So let's run this for function 1. Let's look at the results after all of this JIT compilation stuff. About here, we can note this down as taking about 0.300 milliseconds to go through all of this. And then when we run this for only f10,000, we can compare the difference. And here we can see it's taking 0.058 milliseconds. So this is clearly taking slower with more functions. If it wasn't slower, I would be concerned that JavaScript is optimizing out our code. And for the sake of it, we can put this halfway through and see the results. I would expect this to be somewhere in the middle, and it seems like it is. This is 0.185. Let's move on to the next language and then show the results at the end. So now let's look at Rust. I've also made the generator for Rust as well. And you can see here I have fought with the Rust compiler quite a bit because Rust keeps trying to optimize my functions away. And here I believe I have results. I have this no mangle and inline never. So we're forcing the compiler to not optimize this code away so we can measure how long it is taking. In this, I got results with it. I have to limit it to about 6,000 functions because we get a stack call exceeded when going for more. And let's generate this. We get the benchmark.rs and we can copy this into our lib.rs. So the way I'm doing this is we are producing a static lib, and this static lib can link to the main.rs. The reason I've done this is because of my fight with the Rust compiler. In this, I've noticed I'm getting results as in when I call the function furthest away from the hello world, it is taking longer to execute than when it is calling the function right at the hello world, so we can see how long the function call is taking. And so to compile the library, I've been using this line, and this outputs a lib.lib or something like that. Lib.lib. And this lib.lib is linking to this main.rs. And when we generate this, we will see. And then we can run the main.exe. And this is taking 233 microseconds. Let's run this a few more times I think the computer optimizes this more somehow with the more I run it. So let's just try to get this to be consistent. And we're getting about 133 microseconds. Let's recompile this, but point to the function that contains the hello world. So F6000, we can update this to call F6000 here and check the speed differences. So remember, we have 133 microseconds averaged out roughly. And let's compile that. And so the first call, we have 195 microseconds. This is quite normal that the first call is always slow. The consecutive calls are about 90 microseconds. And if you are curious about learning more how the Rust compiler is optimizing code, you can check out this godbolt.org compiler explorer. And this shows the output of what is being compiled. This is quite a useful tool. I was using this when I was fighting with the compiler and adding the decorators such as the no mangle and the inline never. So I would recommend it. Great tool. And last but not least, let's check out Python. We have generated this code generator, and unfortunately, it seems like 600 is the upper bound before Python seems to have some kind of stack overflow. It thinks we're doing some recursion, and it says recursion error if we have too many functions. So I've limited it at 600, and we have the same kind of logic. And we can generate this with the command python3 python.py, and this is outputting benchmark.py. And now we can copy this into the Python project, and here we are. Just copy and pasted that, and we have a print at the end, and then we can see how long this takes. You know what? Let's average this out. This is too random for my liking. So I've gone ahead and modified this code to average it out because the results were quite random, to be fair. Getting a 0.06, 0.08. It's about 0.085 milliseconds. Now let's call the function where the hello world is and compare the results. Okay, and so now let's go over the results. They are seeming to make sense. This experiment was not fully scientific. It was not fully comprehensive about every language, every metric, everything that can go wrong. But I think we have a very good overview of how long a function call takes. So for JavaScript, one call for the hello world takes about 0.058 milliseconds, and then 10,000 takes 0.3 milliseconds. So we can subtract this initial call by how long it takes for 10,000 milliseconds, and which will get us to be 0.242 milliseconds for those 10,000 calls. And then we can divide that by 10,000, and then we get ultimately 24.2 nanoseconds per function call in JavaScript. And this is good. This is making sense. 24 nanoseconds is fast. And let's move on to the next language, which will be Rust. In Rust, one call takes 80 microseconds, and then 6,000 calls takes 133 microseconds. Subtracting those two numbers, and we get 53 microseconds for the 6,000 calls. And then dividing 53 by 6,000, we get 0.008 microseconds, which is about 8 nanoseconds per function call. This is cool. This is interesting. We can see Rust is faster than JavaScript, which makes sense, and this is exactly how much faster. If you see any mistakes in these calculations or anywhere, please, the code is going to be on the GitHub. You can make an issue there, or feel free to leave a comment below and just complain about me. Maybe I'll make another video if there is something wrong. And let's look at Python. Python, one call takes about 0.05 milliseconds, and then 600 calls takes about 0.085 milliseconds. Subtracting those numbers, we get 0.035 milliseconds for the 600 calls. Divided by 600, and it will take about 58 nanoseconds per function call in Python. And once again, if you find anything wrong with these results, please let me know, and thank you for watching.